So, good morning. In our previous lesson, we had a look at texture mapping, which is basically uh, the creation of textures on graphics. In other words, giving our graphics textures. After we have done the lighting, effects, we can now put a texture on our graphics by doing texture mapping. This can be done either by defining text cells in an array, or we can do it by sampling. Means we pick a graphic that is taken using a digital camera, and then we sample that graphic and map the same texture it has into a graphic that we have done using computer graphics. That is done, of course, by first of all studying or sampling that graphic, converting whatever its content are into the text cells array, and then implementing that text cells array on our graphic. And we have seen quite a number of we had a demonstration of this mapping within this diagram that we looked at here, and I requested you to go through this so that you can have a chance to appreciate what is it that we do when you're talking about texture mapping. So now in this lesson, which is the last lesson of our course, we are going to discuss about ray tracing. Ray tracing is the epitome. It's related to raycasting, and is the epitome of computer graphics. Is the cream de la cream of computer graphics. The most recent, one of the most recent algorithms that are used in computer graphics is the ray tracing algorithms. And I also would like to take this chance also to say that computer graphics is what we are doing in this unit is actually at the very conceptual level. Is like introducing ourselves to the concepts, because then if we are just to have a little bit of more exposure into this computer graphics area, we'll be able to appreciate how rendering takes place, eventually the kind of effort required when you have a rendering farm, and those farms that produce what we call the animated movies. You see the amount of computing resources required. You need a myriad of computers, many computers, to just do a simple video because of the amount of processing required. It's kind of a supercomputer. So this kind of an arrangement is what eventually creates what we see as animated movies. Is an effort that is coming from computer graphics. Ray tracing is one of the most recent techniques that have been used. And probably before I get into the concepts that you're seeing here, I would like us now to visit the origins of this ray tracing. If we go a little bit back, sorry for this, I would like us to look in Wikipedia, this diagram from Wikipedia. There's a gentleman called Albert Dürer who introduced ray tracing. This is in 1587, I think, or not wrong, 1587. This guy shows people. You can see the image. You can see the man here working on this. Look at the kind of attention he's giving to the details. Of course, there is a grid here which is using to study this image. I don't know whether this is real life. I don't know whether it's a woman lying down, and I don't know if it has to be a woman. It's fascinating. That has been the game in the world. If a man is not thinking about God, most likely he's thinking about a woman. It's natural. If you find yourself in that situation, don't blame yourself for being a man. So this man is busy drawing the image of this woman. You can see his hand, but you can see where his eye is. He's trying to trace the ray that is coming from this reflection to his eye, backwards, tracing it, finding where does it land, what color is it, so that he can do an image here on this paper that is exactly like what is here. This is the first effort towards ray tracing. And then now we had in California a gentleman who created a flipbook animation, and I think we have seen this flipbook animation. There was a time they were on sale. That is in the late 80s. It was a technology, those times even color television were not there. For your information, they had not arrived in Kenya. But we, as children then, because I was a young boy, we used to have these flip books where you could see a movie through flipping pages. But of course, it was not at the speed you are seeing here. So I don't know. Some of it was converted into things we could view using. We bought things that we could view, like the way like a camera. You watch a video, like a gadget that we used to watch this kind of flip-flop animations. Is a kind of animation movies we used to watch that time, and they used to take this saw. Take note why we call them flip-flop. If you observe closely, you'll discover that these are pages, different pages moving very fast. 34, 39, 42, up to 42. 1 up to 42. is creating the effect we are seeing of this human being moving. You can see that. Look at the numbers changing here. So this is animation, a flip book that was created in 1976. It is from this actually, it is from these efforts that today we have computer graphics. So today, if you have an idea and it doesn't seem to work the first time the way you wanted it to, don't give hope. That a simple idea, long after you are dead or I am dead, will be what people will be enjoying and eating from. The thing is, you have to know how to transfer it to the next person who is interested as you are. And that's why in school, anyway. This is what the white man has succeeded in doing. I mean, the Western world. So, and the Chinese world is following suit. I think Africa has been asleep for some time since they last discovered the fighting horses of Pharaoh or Pharaoh, those early days. Anyway, that's a by the way. So, how does this work? Now, we have seen the flip-flop. Now, in modern days, in modern times, with the computing power we have, how does it work? What is ray tracing? This is what I would simply describe it. In computing, in real world, what we do is that we put some light in a room when you're creating a video. Even when you go to when you go to how do you call them? When you go to a studio for some photo shoot, what do? They first of all place you where you should be for the best photography. They ensure you are properly dressed. You are now this object. You are placed within the within the studio room. Then they place some light sources. Some of these light sources will come up at the same time when they will be taking the photo. So they place the light sources in position and find a way of focusing them so that they will not shadow. In your case, in the case of there will be no shadow in that image, so that it comes out very clearly. We don't like shadows in our passport photos, for instance. So to remove those shadows, you've got to have several light sources in the room, and those light sources should go together with the flash of the camera. So when the person in the studio, the person in the studio presses the button and the camera shoots the picture, at the same time the flash comes out and the other light sources also light up, then you're able to see a very clear picture. Very clear picture. And that's why you go to the studio when you want a very clear picture, because there will be no that shadow. It will be you as you like to be seen. How do we create the same effect in virtual? Remember, this is a virtual world. So we have a light source here, and you place a light source somewhere, and then you have a camera on the other end. Remember, this is a virtual camera. It's not a real camera. We have now moved into the computer graphics area, where everything is virtual. We call it virtual cinematography. If we put this light source and then try to study the effect from the camera end, there is so much light rays that get lost. I mean, we are unable to determine the color that appears on this surface properly, even with the ambience, the diffusion, and the whatever specular we discussed earlier on. It becomes a lot more easier for computer graphics to work it out the other way around. In other words, it becomes much easier for us to have a situation where the camera and the lighting, we work it out. We trace the ray from the camera side all the way to the light source. The idea is, when you trace the ray from here to the object surface and then to the light source, it becomes easier to compute what this pixel, the color this pixel should be, given the overall color scheme of the object. What should be the specular, the ambience, whatever. The color of this, the intonation is created perfectly. So that is the idea behind ray tracing. And it is quite some time, and I would like us now to look. Probably I'll be sharing this video with you. This video is by a lady called Susan Fong, who is a rendering technical director at Khan Academy. They produce animation movies. I don't know if you can listen to just a bit of it, and then we can pick it up from there.
Hi, my name is Susan Fong, and I'm a rendering technical director here at Pixar Animation Studios. My job is to make sure that the images you see in the theater are created as quickly and efficiently as possible. Now that's a big job, because as Christoph described in the previous video, rendering is an extremely complicated process, requiring thousands of computers, all working together to render our films. The render farm is where we keep all of these computers. What are these computers doing exactly? That's the topic of this lesson. In the first part, we'll take a geometric look at how a renderer works. In the second part of the lesson, we'll look at some of the equations and algebra that are needed to write a renderer as a computer program. So, let's get started. Let's start with a drastically simplified scene from up. This object looks in 3 dimensions, as we can see as we navigate around it. Just like live action filming, you need to place a camera inside the scene. In computer graphics, we call this a virtual camera. You first pick a location for a virtual camera that will be used to create the image.
Now I think the rest you can study by yourself. I'll be sharing that video. There is a lot, in fact, as you can see from this end. You see rendering, you see what is ray tracing, you practice. And I would dare say this, that what you're doing in computer graphics is really introducing the concept. There is so much that we need to learn that we could spend another semester and another one probably just doing computer graphics unit semester by semester for us to be at the level where you can be able to produce this for commercial purposes. I mean, it ought probably to be a specialization in computer science that has not been, produced so far. But so be it. We're in this situation where you're only doing one unit in computer graphics. It's probably giving us a test that in the way you can be, you can test some juice and then later on you expect to be given a class. But this class does not come in our case. So let us test the juice. At least we get to know how it tastes, so that out there we can be able to talk about its test and it can arouse our interest to delve further into the area of computer graphics, animation, movies, and all that there is in graphic manipulation. Well, having said that, now I'd like us to go into the content that you have to cover in a very brief way, and I'm avoiding to use the word shallow, so that we have the concepts that we need to use in computer graphics. Ray tracing. So we first start by asking ourselves, now we have an idea of what ray tracing is. It's basically a rendering method that follows rays of light backwards. We have seen that. Rays of light backwards to eventually find what color they are is a technique for higher quality graphics. Rays may be launched recursively when the color of a point of an object depends on incoming light from a specific direction. For example, when a ray hits a reflective object, a recursive ray is launched in the direction the reflected ray is coming from. In ray casting, for each pixel in the viewpoint, cast a ray from the eye position through the point in the eye coordinates that maps to the pixel center. Intersect the ray with all objects in the scene to find the point closest to the eye position and apply the illumination model at that point. This technique is used to produce 3D computer graphic images, and replaces the Z algorithm. And of course, it's much efficient but computationally intensive compared to the Z buffer algorithm. We have a number of limitations in ray tracing. While ray tracing works well for for point lights and directional lights, it can't handle area lights. An area light is one that has area. Ray tracing uses shadow rays to tell whether a light source illuminates an object, but a shadow ray is cast in only one direction and can only hit one point on an area light. Ray tracing doesn't take into account illumination by reflected light. I mean, ray tracing does not take into account an object that is illuminated by light that has been refracted from another object, as opposed to from the source. Like the way the moon works, it doesn't take into account the light that is the moon. We have the concept of intersections. We have two concepts here. Geometric objects intersection. The intersection of geometric objects is a set of points, part of the plane or space they have in common. In lines, when you have lines, two line segments can only intersect if their y span have an overlap and they are adjacent in the x order, and that y coordinate. They are horizontal neighbors. In mathematics we talk about the y-intercept. Y is equal to mx plus c. Why is the y-intercept there? Is it m? Or is m the gradient? You remember the story of the y-intercept. Now the scene signature. The larger image structures such as windows, signs, or doors offer more hope as they capture shape and texture on a broader scale. Such texture forms scene signatures. They can be reliably matched under large variations in appearance, thus opening the door to robust localization. The benefit of using scene signatures instead of low-level point features, which look for corners, edges, or blobs, is that the data-associated problem becomes less challenging, since the scene signatures are very distinctive. They focus on the doors, signs, windows, not on particular pixels. Of course, they still zero down to pixels. Efficiency with regard to ray tracing. Because material properties are part of the state, if we change materials for many surfaces, we can affect performance. We can make the code cleaner by defining a material structure and setting all materials during initialization. So we set the materials during initialization by using this, defining the structure. You know about structure in C. They define structure, material structure, then GL float, ambience, its diffuse, its specular level, its shyness, and then of course we define this the name of the material structure. This is what we call the object in programming. In this case we call it a variable of this structure. Now the ambience, the diffuse, the specular is defined using these arrays as 4, this is balanced at 4 anyway. The other aspect that we have come across, we have come across this aspect in in the previous lesson, surface normal. Now we see the surface normal, the intersection point. Now that we have seen the intersection points here at these intersections, the surface normal at that level. A good surface intersection technique has to balance 3 conflicting goals: efficiency, robustness, and accuracy. Remember we talked about form and accuracy and shading, and here we use the shading. It determines the color for each field pixel. Texture mapping describes shading variation within polygon interiors, and that we have covered in texture mapping. And we found that the easiest way for texture mapping is actually through sampling, where you take an image that is digital, map whatever is in that image to the graphic that you have, through of course sampling that image and creating the necessary textile array for implementation into the new graphic. Choosing a color for each pixel will require each elimination calculation for array from the eye point through the viewplane provides a radiance sample. Then the other question you could ask yourself: how do we choose where to place samples? How do we filter samples to construct image? And we have seen steps in OpenGL shading, where we enable the shading and select the model using GL enable, specify the normal, specify material properties, and specify the lights. And I think this is important for purposes of this part is important because we are building on this. We are building on this shading. We are building on the concept that we have learned previously for us to be able to understand what happens in ray tracing. But basically now we appreciate the concept of ray tracing even from what we have seen as I was explaining the origins. If you cannot revisit it briefly, you can see where it started. And still, artists still use this. I mean, they use tracing papers today. You know that. Tracing papers. And they get the same. The idea of ray tracing is borrowed from tracing papers. Imagine how hard it is for you to take a photo, observe it, and draw it on a grid. Some artists still do that. It is much easier to take the photo itself, place a tracing paper on top, then trace the object, and then after that, trace it on another paper you intend to draw and draw it. That image is going to be a map of what you expected. It's like going to be a photocopy. Now from there we had the flip book, and I told you that this is what animated movies when we were young. The mid-80s, mid-80s. You can see this flip book is basically, these are pages, 1 up to 42 pages, creating the effect you're seeing here. That's why at the top you can see numbers running here. And then of course today we have this. Instead of putting the light source here and then a camera here and seeing what the light source is producing, put the camera here, put the light source here, study each ray with regard to this object so that you don't have to waste too much light rays studying them. Study each ray that bounces on this object and trace it backwards. That will determine the color at this point. And if you want to know how that is done, we have labs that do that. We call them the rendering farms, just like we have software farms. We have render farms for producing what we call animation movies, and I'll be sharing this for you to listen. It's an interesting thing, and you can go through all this. Some of you I know have an interest in computer graphics, animation, and so I'll be sharing this with you so that you can appreciate. Thank you so much, and I wish you the best. Now I want to say that we're also going to have a quiz. This quiz you're going to have is going to cover the parts of this lesson that you have not covered so far. The last quiz covered lesson 4 and 5. So the quiz you're going to have now is going to cover 6, 7, 8, 9, and 10. And I would expect that quiz will be submitted on Monday, so that we possibly can have a face-to-face meeting where, God willing, on Tuesday I'll be in Karatina main campus, so we could meet briefly for about 30 minutes to just sensitize you on what to expect and guide you towards how to revise, given that this is going to be this unit can carry you away if you study it outside the concepts which are here. You can see, or it can carry you away. You can find yourself spending hours and you plan to do 2 hours. I want to give you a revision guide of some sort, but I expect you to have finished. And that this quiz that I'm giving here is going to be equivalent of Cat 2. No one should miss it. By Monday, they should have submitted it. Thank you.